valence shell electron pair repulsion theory. This theory comes after the valence bond theory, and it mainly deals with the shapes or geometries of the polyatomic molecules. See, the Lewis concept only explained the reason why the atoms combine with each other to form the molecules, and it failed to explain the structure or the shape or the geometry of the molecular species, the nature of the bonds, types of bonds, and how these molecules are formed. So these are the few things which the Lewis concept was not able to explain. Then we switched to the valence bond theory, where we only came to know about how the molecules are formed, how the atoms are actually combining with each other to form the molecule. But then again, the valence bond theory talks about only or explains the formation of diatomic molecular species. Whenever it comes to the polyatomic molecular species, it doesn't explain that how the polyatomic molecular species combines, as well as it's failed to explain their structures or geometry. So we move to the valence shell electron pair repulsion theory, which was actually given by Powell and Sedgwick in around 1940. This was later on much more modified by Gillespie, and that's why this is regarded as one of the best theories in order to explain the geometry or the structures or shapes of the molecular species. Now this theory is based on certain facts. This theory already accepted that the molecular species are existing in the different molecular structures like linear, trigonal, planar, tetrahedral, trigonal bipyramidal, octahedral or square bipyramidal, pentagonal bipyramidal, etc. and etc. Now, what all these postulates of the theory are? Now, according to this theory, every molecular species has a central atom around which all other atoms are arranged. Around which all other atoms are arranged. Now this central atom usually have least electronegativity. Now, second point, second postulate, the shape of the molecular species depends on the number of pair of valence electrons present with the central atom. Third point, these pair of valence electrons, arrange them around the central atom in such a way that they have minimum interelectronic interactions between them. This is most important line, because we must know like charges repel each other. The small central atom will have many valence electron pairs around it, which are to be arranged. Valence electron pair means they can be bonded or they can be lone pairs. So now this central atom arranges these pairs in such a way that in the three-dimensional system, so that they have minimum interelectronic repulsions, or we can say maximum stability, because or minimum energy. Now in doing so, that's the fourth point is, now in doing so, the species attains different shapes. Now the most important, always these interelectronic repulsions of valence electron pair are in which order? Are in the order lone pair repulsion is maximum because lone pairs are free to move, followed by lone pair, and the least is between bond pair. And so always the central atom tries to minimize these repulsions, and in doing so it attains different shapes or geometries. This is the most important thing in this point. The next point, the multiple bonds are considered as single pairs, and by considering them the single pairs, we arrange these pairs around the central atom so that different shapes or geometries are attained. Now let us see how we predict the structures or the shapes of the different molecular species as per this theory. Now the basic of this theory is, we classify the valence electron pairs into two categories. The one are called bonded pairs and another are called lone pairs. They both together decide the geometry of the molecular species. Remember, in the geometry we include both of these, whereas in shape we include only the bonded pairs. And this is how the shape of the molecular species and its geometry differs. Now let us study with the examples at how we predict the structures or the shapes of the different molecular species as per the VSEPR theory. Now let us study how we can predict the shape or the geometry of the molecular species as per the valence share electron pair repulsion theory. In this, A is taken as a central atom. We will study how many number of electron pairs does this A central atom is having, out of which how many are bonded pairs, which will be called B, out of which how many are lone pairs, which will be called E. What are the common examples we have with this type of a system? What will be the shape of such molecular species, and what will be their bond angles? So let us start with the number of electron pair 2. So this is the first case we have. And let us take example in which both the bonded pairs will be what? Both the pairs will be your bonded pairs. So it will be 2 here. We can say this type of a molecule as AB2 type. B means A is the central atom and B are the two bonded pairs it is having around it. No lone pairs. Example, beryllium chloride. Beryllium has two lone pairs. Sorry, two electrons, two valence electrons. Both valence electrons are shared with two chlorine atoms. So how many bonded pairs this chlorine is having? 2. Now try to find out this one. This central bromine is now having two bonded pairs. Now these two bonded pairs can be present anywhere, but definitely they will have what? lot of interelectronic repulsions. When these repulsions will be minimum, when these bonded pairs are maximum distance apart from each other, and due to which, do you know what happens is, this rotates and comes here. That's why this is not the exact shape. What we get is, the exact shape comes out to be beryllium here, and we can have chlorine, and this angle becomes your 180 degree, shape becomes linear. So geometry is also linear, shape is also linear, and the angle is 180 degree. Because by doing so, this beryllium has arranged its two bonded pair in such a way that they are having minimum interelectronic repulsions. And that is why always, whenever the central atom will be having two bonded pairs, the shape will always be linear. The other examples of the same category can be your like ZnCl2, etc. Now let us move to the second other example. In this we cannot have A, B, E category, because if there are two atoms only, we don't have a third one, we cannot predict the shape or geometry of the molecular species. So let us move to the second type, in which we will be having three pair of electrons with the central atom. Three pair of electrons, out of which, let us take first example, all three are bonded pairs. So we are considering example of A, B, three molecular species, no lone pairs. Example are BF3. See, now you can easily see this one. This is the boron. Boron has three valence electrons. All three are bonded to three fluorine atoms, so boron is having three valence electrons. Now, like suppose there are two pair already. If we have a third pair also of third fluorine, what will happen is, these three fluorines will have what? An angle of 90 degree, so they will face a lot of repulsions. So they bend this bond towards this side, they bend this towards this side, so ultimately the shape is not like this. What the shape becomes is, the shape becomes like this. It becomes boron, fluorine, fluorine, and this is the fluorine. So the shape is trigonal planar. We call it trigonal planar. So the shape is trigonal planar, and each angle is 120 degree. 360 divided into 3. So this is what is your BF3 is. We can have other examples like BCl3, AlCl3. All these will be having this kind of trigonal planar structure. Now, we can have one more variety of the molecular species in the same category. It will be the same molecular species with three pair of electrons, out of which two will be the bonded and one will be the lone pair. And the molecule will be called type AB2E. We call it this type, AB2E. The best example we can have is your SO2 molecule, sulfur dioxide. See, sulfur has 6 valence electrons. Out of these 6, we know each oxygen requires 2. And we know that the basic of the valence shell electron pair repulsion theory, that all multiple bonds are to be considered as one pair. So what we notice is, each sulfur is taking what? The sulfur is giving 2 electrons to this one oxygen, one dative bond to this one oxygen. So it is left with what? One pair. So in this case, what we find is, though the geometry remains trigonal planar, what we find is the angle, the shape is not trigonal planar. It is, we call it V shape. We call it V shape. And in this case, what we find is, the angle will also be slightly less than 120 degree. Why? Because remember, these lone pair, bond pair repulsions are stronger than these bond pair repulsions. You know, one can easily think over this, like why these two oxygen cannot be very close to each other. The reason is these bond pair also have repulsions. Why they can't go beyond this more than the angle this one? Because this lone pair bond pair repulsions are there. So since these lone pair bond pair repulsions are more stronger than the bond pair, what we find is this angle will be less than 120 degree. So angle in this case is less than 120 degree. Shape is V shape. So this is what are the examples or types possible in case of the central atom having 3 pair of electrons. Let us take now the molecular species in which the central atom is having 4 pair of electrons. This is the third category we have. And let us take first case in which all 4 of these are your bonded pairs. No one is the central atom is having no lone pair. So it will be AB4 type. The best example is like methane or CCl4 or SiCl4, etc. Now we can know very clearly, see now till the case where the central atom is having 3 pairs, the molecules remains 2-dimensional, remember 2-dimensional. But the moment the central atom acquires 4 pair of electrons, the molecular species becomes 3-dimensional. How? Let us see this. Say let us take the first case like we have taken the boron trifluoride. Let us take, if suppose in case of boron we are having carbon with not 3 fluorine, with 3 hydrogens. Now from where to accommodate the 4th hydrogen? If the 4th hydrogen comes from like from this side, this 4th hydrogen, this angle of 120 is divided into what? 60 degree. Now these will have strong bond pair repulsions. That is why this is not very stable. So what happens is till this molecule is till it is having 3 bonded pairs, it is planar. Now what happens is the 4th bond comes from the top, and this bond bends the other 3 because these will repel, it bends it downward. So as a result, what we find is the structure of the methane becomes what? Like this. It is almost as like this. We call this as tetrahedral structure, in which each angle is of 109.5 degree. All angles are same, and this is one of the very most important and symmetrical structures we have been knowing. The diamond is also having a tetrahedral structure. That the carborundums are having a tetrahedral structure. So what are the angles in this case we are having? It's 109.5. What is the shape called or geometry called? Tetrahedral. We can draw this tetrahedral molecule in 3-dimensional system like this. And then what we do is we draw a bond like this, and we draw a bond like this. Always remember, this is called wedge shape formula. This is called wedge formula. Now in this, always remember, these 2 bonds which are on the plane of this whiteboard actually are considered to be the ones which are actually at the not drawn with the normal lines, are on the plane of this board. The bond which is drawn with this thick line, wedge shaped line, is towards you like this. It's like this. Towards you. And the bond which is drawn with this dashed line is actually away from you. It's like this. It's on the other side of this whiteboard. So this is how we draw the 3-dimensional structure of the tetrahedral structure molecules. Let us see the other case in this case. The case is the central atom is having 4 electron pairs. Now with the same 4 electron pairs, let's have a case in which the central atom is having 3 bonded pairs and 1 lone pair. So it's a case of AB3E. The best example can be your ammonia molecule, phosphine molecule, PCl3 molecule, etc. Let us take ammonia. Nitrogen has how many valence electrons? 5. out of which how many are bonded to hydrogen? 3. So 3 bonded atoms and the 2 electron left makes it 1 lone pair. So 3 bonded, 4 lone pair. Category is this. Geometry will remain same, tetrahedral, but the shape will change. How? See, this out of the 4 bonds, nitrogen is forming what? These 3 bonds. The 4th bond is actually like this in the form of a lone pair. So what we draw is the shape is not tetrahedral, it is pyramidal. And do you know what happens is we get what? A strong bond pair, lone pair repulsions. Bond pair, lone pair repulsions. As a result, these angles become shorter than 109.5. Like in case of ammonia, it's 107 degree. It's 107 degree. It's less than this. So in this case, the angles are of course less than 109.5 degree. So this is one case when we have a 3 bond pairs, 1 lone pair. Shape is pyramidal, geometry is tetrahedral, angle is less than 109.5. In case of ammonia, it is 107. Same will be the shape of phosphine PCl3, and such molecular species which are having same shapes are called isostructural molecular species, are called isostructural. So these all are isostructural. Let us take one more case in which we have 2 bonded pairs, 2 lone pairs. We call it AB2, E2. The example is water molecule, H2S, etc. Now you know oxygen is having 6 valence electrons, out of which 2 are bonded to 2 hydrogen atoms. So 2 bonded pairs. The 4 electrons left are forming 2 lone pairs. So oxygen, and these are the 2 hydrogens it is having. The other 2 pairs of electron lone pair are present like this. So the shape we call as bent shape. Why bent shape? Because this molecule has, you can see with this one, like it has both lone pair repulsion, it has lone pair, bond pair repulsions. So that these repulsions bend this water molecule like this. This angle becomes very small, it's 104.5 degree, very less than your 109.5. Why? Because it has 2 types of very strong repulsions. And that is why water and H2S are called isostructural species. They both have bent shape. So geometry is tetrahedral, shape is bent, angle less than 109.5. In water it is 104.5. So these are the cases when we have 4 electron pairs with the central atom. Now let us take the example of the molecular species in which the central atom is having 5 pair of electrons. This is the 4th case. Let us take the examples in which all of these 5 are their bonded pairs. None of these is a lone pair. So it's an example of AB5 category. Best example is PCl5, PF5, etc. Now see, we have already seen this, that like suppose I am taking this example, if PCl4 we have in the tetrahedral shape, from where the 5th chlorine will come, if it comes from any angle, it is going to bifurcate this 109.5 degree angle into what? Half of this. That will make strong bond pair repulsions. What happens is, what we notice in this case is that of course the 5th chlorine comes from downward side, and due to this chlorine, the 3 chlorine atoms, they face a strong bond pair repulsion, and what happens is they become straight like this. So as a result, what we find is the shape becomes this phosphorus it becomes like this. We call this as trigonal bipyramidal. The shape is called trigonal bipyramidal, and it will be having two types of angles. This angle is 120 degree, and this angle is between the equatorial chlorine atoms. So see these chlorines which are like here, this one, and this one. These three are called equatorial chlorine atoms because they are present almost at the equators. If we consider this to be a spherical ball, these three chlorines will be called present at the equatorial positions. And these two top and bottom chlorine are called axial chlorine atoms. So they are called axial. So the angle between two equatorial chlorine atoms is 120, and the angle between equatorial and axial is 90 degree. So in this case, the angles are 90 degree and 120 degree. What is the shape is trigonal bipyramidal. What is the geometry is trigonal bipyramidal. And this is what is the shape of the PCl5 is. Trigonal bipyramidal. Now important thing to note in this case is, in this case, what we find in this trigonal bipyramidal is that the phosphorus chlorine axial bond length is longer than the phosphorus chlorine equatorial bond length. Axial bond lengths are longer than the equatorial bond length because see, this axial chlorine is facing repulsion from how many other chlorine atoms? It's from here, it's from here, and it's from here. So it's facing repulsions from 3 equatorial chlorine atoms, so it goes a little bit away from these 3 and phosphorus atoms. So that's why phosphorus chlorine axial bond length is longer. Similarly, the downward chlorine is also facing repulsions from these 3 chlorine equatorial. So it goes down. So that's why phosphorus chlorine axial bond lengths are longer than the phosphorus chlorine equatorial bond. This makes PCl5 unstable. That is why very easily it decomposes to give PCl3 and Cl2 or give fumes of HCl the moment it comes across without moisture or it is exposed to air. Let us take now the second case. Second case of the type in which the central atom is having 5 pair of electrons. The second is there can be 4 pair of electrons. 4 of them are bonded, 1 of them is lone pair. So it will be AB4E. And we can have the best example, SF4, sulfur tetrafluoride. Now what is this is? See, sulfur is having 6 valence electrons, out of which 4 are bonded to the fluorine. So 4 bonded pairs. 2 electrons are lost, that will form 1 lone pair. So total pairs are 5. So geometry will remain trigonal bipyramidal. But what happens is the shape will change. The question comes is, the 1 lone pair which is present in this molecular species will go where? Either in equatorial positions or in the axial positions. We know any species or any molecular electron pair or any atom if it is present at the axial position will face repulsion from the 3 equatorial atoms. Whereas if any atom or a lone pair is present at the equatorial position, it will face repulsion from only 2 axial atoms. So lesser repulsions are present at which position? Axial position, equatorial position. So that's why we always find lone pairs to be present in the case of the 5 electron system at equatorial positions. So we get the structure almost like this. This is the lone pair. Now this shape is called, this is the shape actually we have. If you turn this, you will get what? A seesaw. That's why this shape is called seesaw shape. Geometry is trigonal pyramidal, of course. Due to these lone pair bond pair repulsions, this angle is less than 180 degree. It is found to be, in this case, 172 degree. They get slightly bent like this. And this is what the system is. See, you can clearly make out from here, this lone pair is only repelling these 2 axial fluorine atoms. If the lone pair would have been here, it would have been repelling 3 fluorine equatorial atoms. then this molecule would have been having higher energy due to more repulsion. So that's why the lone pair is kept by this molecular species, by this central atom, only at the equatorial position. So this is what is called the seesaw shape 4-1 system, in which there are 4 bonded atoms and 1 lone pair. Let us move to the second type of system. Now let us see the third case, in case of the 5-electron system with the central 5-electron pair system with the central atom. Now in this case we will be having 3 bonded pairs and 2 lone pairs. So it will be AB2, sorry, it will be AB3E2. The best example we can have is, it can be of BRF3, bromine trifluoride. Now you know bromine is having 7 valence electrons. Out of those 7, 3 goes to the 3 fluorine atoms, so there are 3 bonded pairs. And the 4 electron left forms 2 lone pairs. So bromine, now you know from the previous example, where these 2 lone pairs will be present at equatorial positions, because then only they are having a maximum angle of 120 degree between them, which becomes larger than this due to lone pair repulsions, and they will be having lesser repulsions if they are present at these positions. So bromine arranges 3 fluorine atoms like this and 2 lone pairs like this. It's like this. So the shape becomes almost T shape. That's why we call it T shape. Of course, these angles are less than 180 degree. And these are the 2 positions of the lone pairs at equatorial positions. These are equatorial positions of your lone pairs. So this is what we have BRF3, the case where we have 3 bonded pairs and 2 lone pairs. Let us take the example, the 4th one in this category, when we will be having only 2 bond pairs, 3 lone pairs, AB2, E3 category. The best example is xenon difluoride. We know xenon has 8 valence electrons, noble gas, then combines with fluorine. Out of these 8, 2 goes to the fluorine. So xenon is having 2 bonded pairs. The 6 electron left forms 3 pairs, so it's 3 lone pairs. Now how this and xenon will arrange these 3 lone pairs so that they can have minimum repulsion? It is only possible when they are present at the equatorial positions. So xenon arranges 2 fluorine opposite to each other at the axial positions, and this is how the 3 lone pairs are arranged by the xenon. Now in this case what we can make out is the geometry remains trigonal bipyramidal, but the structure of the shape becomes linear. So it's called linear. Angle is 180 degree. So this is what we have, the last type in the category of 5-electron pair system with the central atom. Now let us move to the cases in which the central atom will be having 6-electron pair around it. Let us take the examples of the cases in which the central atom is having 6 electron pairs. Now out of these 6, let's take the first case in which all of these 6 are the bonded pairs, none of these is a lone pair. So it's an AB6 type. Best example is sulfur hexafluoride. Now in this case we know sulfur is having 6 valence electrons. All of these 6 are actually bonded to 6 fluorine atoms, so sulfur is having 6 pairs. Now we have to see here, if sulfur is like this, it's having already 5 fluorine, suppose, arranged like this. From where the 6th fluorine will go? Remember, the 6th fluorine cannot come from the axial positions because it's already occupied by the 2 fluorine. So there's only one choice, it has to come from the equatorial position. So that's why the equatorial position changes, and now in place of 3 it will be having 4 fluorine atoms. So that's where the shape becomes not trigonal bipyramidal, it becomes square bipyramidal. So that's why the shape or the geometry in this case is almost like this. That sulfur is here, and this is what is the system is. We can draw it like this. We say these are, now in this case, this shape is called square bipyramidal. It is one of the most stable and symmetrical structures we have, because we don't have in this case equatorial or axial fluorines. All 6 fluorine atoms are at the equal distance from the sulfur and all angles are 90 degree. All angles are 90 degree. Because if you want, you can take these 4 fluorine as equatorial, you can take these 4 fluorine as equatorial, or you can take even these 4 as such your equatorial. So this becomes almost like this, that the central sulfur is surrounded by 6 fluorine and they take the form of a spherical ball around it, and that's why SF6 is one of the very stable molecules we have, very inert in nature due to the presence of 6 fluorine atoms around it. So this is called square pyramidal structure, which is also called octahedral shape. Octahedral means the structure which is having 8 faces. So this is one category. Now you can make out from here, if we have in this kind of a shape, I can make it out this another time for you people. Like let's see, you can see here, these are the 6 fluorine atoms we have. If suppose the sulfur is having one lone pair, the sulfur will always try to keep this lone pair. It can keep anywhere, because any position, now in this case all are symmetrical, so 6 positions, any can be equatorial, any can be axial. But yes, in order to give a proper shape to the molecule, we try to make this the lone pair always at what? Axial position, so that we can make out easily what is exactly the shape is. So now let us move therefore to the next category of the molecular species, in which under the same heading 6 pair of electrons, in which the central atom is having 5 bonded pairs and 1 lone pair. So it's A, B, 5E category. The example can be bromine pentafluoride. Now this bromine is having 7 valence electrons, out of which 5 are with the 5 fluorine atoms, so 5 bonded pairs. 2 electrons left will make it 1 lone pair. So how these 5 are arranged by the bromine? They are arranged in the what? Square shape. 4 arranged in the square shape. 1 fluorine is on the top and 1 lone pair is at the bottom. So that's why what we say is the shape is only, it's square pyramidal. It's not bipyramidal, because here we have a lone pair. So geometry is square bipyramidal, shape is square pyramidal only, and the angles exactly definitely will be less than slightly, these will be slightly bent towards upper fluorine, so it will be less than 90. But these, of course, slightly less than 90 degree are the angles. But this is what is the case we have in this category. Let us take the next case, where we will be having 4 bonded pairs, 2 lone pairs. The categories AB4, E2. Best example is xenon tetrafluoride. Xenon, out of the 8 valence electrons, 4 are bonded to 4 fluorine atoms. 4 electron left makes it what? 2 pairs, lone pairs. Now, how these xenon arranges these 4 fluorine and 2 lone pairs? It makes this 4 fluorine to move at the equatorial positions, and 2 lone pairs are kept maximum distance apart from each other, so that lone pair repulsions are minimum. And in doing so, what? The xenon acquires what? Only square planar shape or structure, whereas geometry remains octahedral. Angles will be exactly 90 degree. So this is what is the cases. We can't have a case in which we can have a central atom with 3 bond pairs and 3 lone pairs, because 3 lone pairs will be now, if are present, will be present like this. They will be having now an angle of what? 90 degree each. Strong repulsions will make that molecular species very, very unstable. So we don't have such kind of category ever existing in this case. So this is what we have the possibilities in case of 6 electron pair with the central atom. Let us take 7 electron system with the central atom. If we have 7 electron pairs with the central atom, all 7 bonded, none of them is lone pair, It's AB7. Example is IF7. What will be its shape is? Iodine definitely can arrange 5 like this, like I have discussed in the octahedral shape. Now where the 6 can be arranged like this, where the 7th will go? The 7th fluorine cannot come from, again, from what, as I have told you, it cannot come from the top, bottom. The problem is that they are already occupied by these. If we take these 2 fluorine as an axial ones, so the 7th fluorine has to come again from the equatorial positions. So it will make again, now in place of 4 fluorine at the equatorial, will be having 5 fluorine atoms. That's why the shape is called pentagonal bipyramidal. It will be almost be like this, like this. A pentagonal is drawn around iodine, and each corner of this is having 5 fluorine atoms like this. 1 fluorine down, 1 fluorine up. So these are called your equatorial fluorine atoms. These are called your axial fluorine atoms. Angles are reduced here from 90 to 72 degree, 360 divided by 5. And this angle is, of course, is your 90 degree. So angles are 72 and 90, and it's called pentagonal bipyramidal. This is what is the structure or shape is, or geometries. So this is a case. Of course, this will be here the bond pair will be having strong repulsions. The molecules are not very stable, but yes, still this molecule exists in the gaseous state. We have one more case in the category in which the central atom is having 7 electron pair. It's the one which is having 6 bonded pair and 1 lone pair. It's called AB6E. The example is xenon hexafluoride. Xenon, out of the 8 valence electrons, 6 goes to the 6 fluorine, so it forms 6 bonded pairs. 2 electrons left forms the 1 lone pair. Now where this lone pair will go? Definitely, if it goes at the equatorial positions, axial position, it will repel 5 equatorial fluorines. That is going to repel much more. And that will create a lot of repulsions, that will increase the molecular energy to a very high level, that will make that molecular species very unstable. So the lone pair is present at the equatorial position. Now how? You can see here, this xenon, out of this 5 fluorine which it can arrange, only 4 are present, and the 5th fluorine, in place of 5th fluorine we have 1 lone pair, 1 fluorine is here, 1 fluorine is here. So you can easily make out, this is your axial, this is your axial, equatorial, 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 and this is what is there. So the geometry remains a pentagonal bipyramidal, the shape changes, and it's called distorted octahedral. Why? Because ultimately, if you see, they take the shape of what? Square. This is one pyramid they can form, and one pyramid downward. So it's called square bipyramidal or octahedral, but it gets distorted because of these bond pair, lone pair repulsions. That's why it's called distorted octahedral. So these are all the possibilities we can have, and the best part of this valence share electron pair repulsion theory is that we can, by knowing the number of valence electron the central atom is having, we can easily predict the shape of the molecular species. See, no other theory tells us exactly what will be the shape. They can tell you the geometry, but they can never tell you where the lone pair will go. It is only the valence share electron pair repulsion theory. Even the hybridization, which we'll learn later on, which we'll learn now, is actually based on this valence share electron pair repulsion theory, because it is a theory which is based on the very simple, very basic fact that it is these interelectronic repulsions around of the electron pair around the central atom, which actually keeps a hold of the molecular species energy, and they are the ones which actually decides what will be the energy of the molecular species, and they are the ones which decides what could be the possible shapes, because these central pair electron pairs are arranged in such a way that these repulsions become minimum. So this is the advantage of this theory, but this theory also has disadvantages. It doesn't explain how the molecules are formed. It doesn't explain the nature of the bonds. It doesn't explain the types of the bond. It doesn't explain the relative stabilities of the different molecular species. it doesn't explain their magnetic behavior, color, etc. So that's why it's still having a lot of problems, but still, because of its very unique property of actually telling us what will be the exact shape of the structure, we regard this theory still now, and that is why it is studied and it is used very normally in order to predict these structures and these shapes of the different molecular species.